and welcome to daily Leetcode challenges from Code Me There. Let's begin our question. Okay, question 106. Construct a binary tree from Inorder and Postorder traversal. Alright, so actually let me pull this up. I have an example of look. Let me quickly go over what's happening here. There's three major traversals, or two types of traversals. A in order, pre-order, and post-order, which fall under the same category. And then the other major type of traversal is the basically this is where depth is prioritized, and these are called DFS, depth first search, where you're kind of iterating over the depth of the tree. And additionally, there is another type of traversal called BFS, breadth first search. Right now, this is asking to reconstruct a tree from an in-order and a post-order traversal, which are both DFS algorithms. You can see here an in-order traversal and here a post-order traversal. Generally, the way to think about this would be in order is left, self, right, left, self, right. So left, left, self, right. And since we just did this left, it would be self, right. This would be left, right, self, right, self. Sorry, left, right, self, right, self. So those are the two DFS traversals that were given. Let's see the question. Given two integer arrays, in order and post order, where in order is an in order traversal of a binary tree, and post order is the post order traversal of the same, construct and return a binary tree. Okay, and here we have an example where we are given a tree. And the in order traversal, as I said before, is left, self, right. So it'd be left, self, and right is its own subtree, which would apply to left, self, right. So we should get 9, 3, 15, 27. 9, 3, 15, 27. Post order is left, right, self. So left, 9. Then you go to the right. The right is also a subtree, so it's going to be 9, 15, 7, 23. Left, right. Now this is left, right, self, self. Left, right, self, self. 9, 15, 7, 23. Okay, and we have another example. This is probably just an outlier. Let's look at the constraints. I already know how to solve this, so take this with a grain of salt that I'm not coming up with this on my own. This is a very kind of famous, I guess, algorithm or famous question where you're asked to reconstruct a tree from given these two different traversals, and I'm going to show you exactly how. The thing to look out for here is under the constraints. This approach that I'm about to tell you isn't going to work if the numbers inside of the tree are repeated. However, in this case, we're seeing that the in order and the post order consists of unique values. Okay, so now that that's out of the way, let's get back to looking at our in order and post order traversal. This would be the red and the green tree. Notice that here the indices actually represent the order in which these nodes are going to appear in the list. So an in-order list would look something like 1, 2, 3, 4, 5. Well, actually, it's going to look exactly like this: 1, 2, 3, 4, 5. But if we were to assign values to these, how would we do that? Let me copy this example right here and this example and show you how it would look like in order and pre-order traversal. So here we have the tree. Let's have it like this. I believe there were two. There were. Let's see. And then this one has another. Let's actually call this A, D, and then within here we have another one which is C, D, E. So this is the same tree, just a little bit redrawn, and here we're using letters instead of indices, because what's actually going to happen here is an in-order traversal would look like this: C, B, D, A, E, in order. Post order, which is what we're given to here, would look like C, B, C, B, I messed up, C, D, B, E, A, C, D, B, E, A, C, D, B, E, A. Okay. The reason I drew this out right here is because the algorithm to reconstruct a subtree works as follows. First, the in order is used as a base, so we're not going to sort of modify that. We're gonna use this as a reference. The post order, as you can see, if you were to take the last element out of the post order and then look to where it appears in the in order search, we would see that it splits the tree up into a left subtree consisting of some values, but the most important thing is that we know for a fact this is definitely part of the left subtree, and the right subtree, E. And then we take again pop the next element off the post order, and we see that it is actually part of the right. And then we pop again and see that it's B. So B being split into the left and the right. What I'm trying to say here is that this is what's going to happen. We pop, let me move this guy here. Postorder. We're going to pop the first element off the first element popped. We find A. We split the whole array into a left and a right. Then we pop the next element, which is going to be 2. We find where this element is in the in-order search and use the same algorithm to card it. However, now we see that there's a condition that's being met that we're only looking at one array or at one element. So actually just draw this into the tree, connect it into the tree, return it as it is already part of the tree. Then we do another one. So 3. This B, we find where this B appears. It's going to appear here. And since we've already marked off this left part as the one that we're only going to be looking for, let's see, how would this work? Like this. We look at the B. We split this off into a left and the right. This part becomes the right, which only consists of D, as we can see here. And this part becomes the left. And so, as you can see, popping off one by one leads us into first finding the current one, the current top, then finding the right, then finding the left, and then of that left, finding the right and the left. So here's the function that's going to help us do this. Return builder. As you can see here, what I've been doing is I've been popping off an element and then looking for that element as fast as possible into the Postorder array. So in order to do that, we need a map from value to index of the in-order traversal. Let's see, val indx is going to be, let's see, the val dx for dx val enumerate in order. So print dx. Let's have this return none. Let's see what this does. Spelled in order wrong. Oops. So this is our map of value to index, and now once we're popping off the post order elements, we can easily identify where that element is in our in order array. So once we have that, let's set left bound and a right bound, which is going to essentially be splitting off recursively this in order array into a left and a right, and then working on it left if left bound is greater than right bound return none. This is the condition of where if we've reached some weird situation where well, not a weird situation, a leaf node is calling builder, we are in a situation where we're returning null. Finally, we start constructing our tree node, which is defined here, a tree node with a value. Now, what is this value going to be? Well, the value is actually Postorder pop. So we've popped the first element out of the post order. We've popped that, and we created a root node out of it. Now we're reconstructing the right side of it and the left side of it. So the right side of it is going to be right is equal to builder. However, here we're building the right side of this tree with this bound. So our index, where we decide to do the split, is going to be gotten from here. So value index, we have an index plus 1, and right bound left is same thing, except that we have the left bound and index and return root. And that should be it, except that obviously for this we call line of in order. And I messed up. This might be, there we go. Did I misspell? Post order pop. So pop of an empty list. Somehow I am this was -1. Sorry. -1. Okay, let's quickly speak through this. Okay, so what am I doing wrong here? I enumerated the in order traversal so that when we're popping off the post orders one by one, I am getting the value and immediately mapping it to the index. I'm also creating a root node and using that root node, root.right, root.left, to populate it by recursively calling builder on the right side of that and on the left side. And there we go. Sweet. Yeah, I don't know, probably not much better solutions anyway. Feel free to use this. I hope the little visual shows it better. For those of you who don't like it, I'm going to resubmit it just simply with this. And thank you for watching. See you later. Bye.